Okay, so let's start. So for module 1, so we have already discussed about data flow modeling. So data flow modeling, so this includes design techniques by using continuous assignment. So we use the assign keyword. Also reduction operators like yung and, not and, or etc. Also, we can use conditional operators. So we have the question mark and the colon operators. For the logical operators, so we have here the and, or, not logic. Then for bitwise operators, so we have here the ones complement, shift operator, so shifting to the right, and shift left operator. So data flow modeling, so for example, given expression, so we can automatically use the assign keyword to describe this expression. So we write assign, then z1 is equals to x1. So this is bitwise operator and x2 and with x3. Then for, let's say, given the what you call this, K-map, so you can map, then the right equation, let's say we have here expression for z, so we have here a prime, c prime, and here we have AC, or that is equivalent to this expression, AC plus A prime, C prime, or that is an XNOR gate. So A XOR C, so this is for XNOR. Then we can use the assign keyword. So assign, that is not, so this is A XOR C. Also, for conditional statements, so let's say given this expression, so if we are looking for the maximum between A and B, so we have here A greater than B, so this is our expression. So remember in your programming language, so we have these conditional statements. We have the true part and the false part. Okay, so let's say this is the true part, of course this is the false part. So given the expression, so A greater than B, so this is our true part. Then this is the false part. So wherein this expression is nested. So this is what we call a nested loop. So let's say this expression so is equivalent to another loop. So we can write it so this way. So we have here nested loop. So here we have again our second expression, A greater than C. So A is the true part, then C is the false part. Then for the false part, so let's say this process, so we have here another expression. So this is again the true part, tapos ito si false part. Naintindihan? So let's say if A is greater than B is true, so it will perform this loop. Then again, it will test this expression. So A greater than C, if that is true, so the output would be A. Okay, so if that is a false, so the output would be C. So let's say A is greater than B is false, so it will perform this function. So again, it will test for B is greater than C. So if that is true, so it will output B. And if this expression is false, it will output C. Okay? So we can also use this expression in HDL. So again, by data flow modeling, so we can use the assign keyword. So that is assign, let's say max. So it's equals to A greater than B, A greater than C, then A colon C colon B greater than C. So compare with, so B is true, C is false. Okay. Then in writing test bench for data flow modeling, we can also use the for loop. So remember in our previous example, so we have applied the use of begin. Let's say this is our test bench, so we use the begin keyword, that we apply, let's say stimulus. Then using, let's say we have, let's say three input or two inputs and one output. Or let's say three inputs or one output, so we can use a register, let's say reg 320. Okay, let's say input vector is our variable, or you can use any variable you want. So I use invec for input vector. So let's say let's say my index start at 0. The input vector, so that is, so this is 3, so that means I have 2 raised to 3, so that is 8, so I need to compare it with 8, then increment. Then format for our output, so let's say we have input A, B, and C. Then that is equals to input vector 30. Then to display the results, so we use, let's say, 10 nanosecond. Then we want to display A, B, C is equals to the output. So this represents the binary output for the 3-input circuit we're describing. Then the output is a Z. So in this format, the output is 1 bit in binary format. Then we have the inputs, let's say A, B, C. Then the output Z. Okay, then begin, end. So this part will produce the same as the one we saw in truth table. So let's say A, B, C, then output is Z. Okay, so we had that kind of example earlier. Okay, so let's have another example for conditional operator. So let's say okay, so example 4, let's say we have this expression Z1 is x1 greater than or equals to x2. Then we have x3, x4. So this is our expression. So if x1 is greater than or equals to x2 is true, so then it will output x3. Then if this is false, so it will output x4. Then again, using a data flow modeling, so we use the assign keyword, then z1 is equals to x1 greater than or equals to x2, then condition x3, x4. Okay? So this is useful, for example, in multiplexer circuit. So let's say we have so we want to design a 2-to-1 multiplexer. So let's say 2-to-1 multiplexer. So for 2-to-1 multiplexer, we have the selector S, then the two input, let's say AB, then the output, let's say K. So this is 0, 1, 0, 1, 0, 1. So input A. Then for the selector, let's say the selector natin is S is equals to 0. If S is equals to 0, the output is A, for example. So this is 0, 0, 1, 1. Then if our selector is equals to 1, so it will output what is in B. So that is 0, 1, 0, 1. 0, 1, 0, 1. So therefore our K, so if we perform it using K-map, so we can derive this expression. This is S prime, select CA, plus if S is equals to 1, select C. So B is selected. Okay. Then again, for this expression, so we can use the assign keyword. Let's say for describing that using data flow modeling again. So let's say module. Let's say the name is MOX2. So the inputs are A, B, S, and the output K. So that is A, B, S, and the output K. So we write input. So inputs are A, B, S. Then output is K. Then we write assign K. So for this expression, we can use the conditional operator. So let's say S is true or 1, it will output, it will select B. If S is 0, it will select A. Okay? So we can rewrite this expression using conditional operator. Okay, so using assign keyword, so that is assign K is equals to, so S. Okay, condition B. B is 1, so true. Then if S is equals to 0, that is A. Then end module. Okay, so that's a simple one. Or if we want to use this expression, so using assign keyword, so that is equivalent to assign K is equals to not S and with A, then plus, so that is or S and B. Okay? So alternatively, we can use this expression. So this is for 2 to 1 multiplexer. So we can also expand it using 2 to 1. So for, let's say, describing a 4 to 1 multiplexer. So the 4 to 1 multiplexer circuit, so 4 to 1 mux, so that is okay, so let's say this is the 4 to 1 mux, 0 0 0 1 1 0 1 1. So let's say if our selector is, so let's say we have S0 S1 is 0 0. So the input is A, 0 1, B, 1 0 is C, then for D that is 1 1. So let's say to get the output Z. So we have S0 S1. Let's say 0 0 0 1 1 0 1 1. Then for output Z, if 0 0, so we have A, 0 1 is B, 1 0 is C, then 1 1 is D. So that our expression Z is S0 prime, S1 prime, or 0 0 selected A plus S0 prime, S1 selected CB plus S0 S1 prime selected CC plus S0 S1 selected CD. So therefore, using assign keyword, so we can use a vector for S. So we have two S. So we can rewrite it using in vector form. So S0 and S1 so can be written as S0 1 or 0 1 S. So that means S0 S1. Okay, so in that order. Then using assign keyword, so assign, so let's say Z equals to, so S vector 0. If S is 0, so we need to choose, if that is true, between C and B. Okay? If that is false, we're going to choose between A and B. So that, let's say S0 is true. So that means 1. So we write S1, then question mark C, D or C, D, C, then colon, so false part 0, so we need to choose between A and B, so that is S is 1, question mark B, BA. Okay? So this is the expression for 4 to 1 multiplexer using conditional statement. But again, you can also use this expression. Simply, you can use this expression. Then for behavioral modeling, okay, any question dito, class?
Excuse me, sir. Wala po na-record ang meeting.
I'm sorry, hindi ko na siya na-record. Di ba na ano ka naman siya sa OBS. Okay, so medyo mahaba-haba yan. So that is for data flow modeling. So we recall the data flow modeling. Now let us recall behavioral modeling. So for behavioral modeling, so modules containing, these are modules containing built-in primitives. Then remember the one we had last time using UDP, kaya lang hindi siya gumana sa Xilinx. And also we can use a data flow construct and some other behavioral construct. Then the initial and always block of statements under behavioral modeling. So let's have an example. So let's say, so yung previous one, so we had the data flow modeling for 2-to-1 multiplexer. So let's say we want to perform that using behavioral modeling. So let's say we have the expression. For multiplexer, we have the assign. Let's say K is equals to not S and with A, or S and with B. Okay, so let's say we want to use this expression. Then for behavioral specification, so we're going to write always. So using always block, so we write the always keyword, so always at. So their input is A, B, and S. So we write A or D or S. Okay. Then we can use the if statement. So if, let's say, S is equals to 0, so what will be the output? So K is equals to A. Then else K is equals to B. Okay? So this one is under behavioral modeling. Then the behavioral modeling for 41 multiplexer. So let's say, so let's say this expression or either of the two. So we write using behavioral modeling. So we can write, let's say, okay, so the expression is, let's say, assign Z. So we use S0, S1. So true part is D and C. Then sa false part we have S1 tapos B, A. So the behavioral construct would be always, so that is always at, so we can use asterisk at this point. So let's say if, okay, so S is equals to, let's say, that is 2-bit, S0 and S1, so we can write 2, comma, code mark D. So two input, 0, 0. So kapag 0, 0, selected C, Z natin is A. Then else, if, let's say our S is 0, 1. So now selected C, B, or the output is B. Else if, let's say S is equals to, let's say 1, 0, 1, 0. So the output Z is C. Okay? Then else if again. So if S is equals to 1, 1, so the output Z is equals to D. Okay? So this one is under behavioral modeling or behavioral construct. Okay, any question with this one? So let's move on to another example. Okay, so behavior modeling. So again, it describes the behavior of a digital system. So it is a higher level of, it has a higher level of abstraction that uses Verilog module containing a mixture of built-in primitives, so UDPs, data flow construct, behavioral construct. So the behavior of the design can be described using, so yung ginawa natin kanina, so that is a procedural construct such as the initial and always block of statements. Then for, let's say, in creating a test bench or test picture for behavioral modeling, so doon natin gagamitin si initial construct. So let's say, so we want to write the test picture. So let's say we want to display output. So let's say we want to display x1, x2, and z1. So we use the initial keyword. So initial, then for the monitor, so we have x1, let's say b, x2, then we have z1 percent b, then x1, x2, and z1. So this one monitors the variables in the parameter list. So we have same as dun sa ating truth table. Then we apply input vectors for this one. So input vectors, let's say, again, we write initial, then begin, let's say at time starting at 0 nanosecond. So let's say we want to input x1, 0, so 1 bit, 0. So let's say x2, we want to input, let's say a 0. So again, 1 bit, binary, 0. Then next, let's say next time frame, let's say after 10 nanoseconds, so we want to input again x1, let's say 1 bit, 1, tapos x2, let's say 1 bit, 1. Okay? So x1 is input 1, x2 is input 1, and so on. Okay? So this one is under the test picture. Okay, so let's have Simple example under behavioral construct. Okay, so let's say given is, okay, so let's say we have a given circuit. Let's say 3 input AND gate with input x1, x2, x3. Then the output is k1. So using behavioral construct, so we write module, let's say AND3 behavioral. So inputs x1, x2, x3, and output k1. So we write input x1, x2, x3, output k1. So we don't have here net, so we don't need to declare net. So let's say meron tayong another circuit here, let's say NOT gate. So we will place a net here. So we can say that is net 0. Then so we need to declare net 0, okay, as a wire. So that is what we call internal wire. Okay? So since wala naman siyang other component aside dun sa AND gate, so we can simply declare wires x1, x2, x3. Okay? Then k1 is our reg. K1. Then using behavioral model, so always add, so input natin x1 or x2 or x3. Then let's say z1 or k1 is equals to, so this is AND gate, so that is x1 and with x2 and with x3. Then end module. Okay? Then for the test picture, okay, so test picture, let's say shortcut ko na lang. So I will start with the use of the initial keyword. So initial, then begin, that apply stimulus. So here I'm using the for loop. Okay, so we have here 4 variables. So my reg is 3, 0. Let's say input vector, let's say I. Then for I starting at 0, then again I have here 3 variables, so that is 2 to the 3 is 8. So compare I with 8. Then I increment. Then begin. So x1, x2, x3. Then I vectors 3, 0. Then let's say time scale natin is let's say for every let's say 8 nanosecond. So it will display, let's say let's include time, time. Then we have here x1, x2, x3. So this is another format. So we use percent %b, percent %b, percent %b. Then we have z or k1 is equals to percent %b. Then for the variables x1, x2, x3, k1. Okay? So begin, then end. So this one will give you the truth table. So in this format, so x1, x2, x3, and the output k1. Okay, so here we have 8 combinations, so from 0 to 7. Okay, so 8 combination. Question, class? Questions? So no more questions. So let's move on to the next one. So if you may recall in your logic circuits class, so you have, I think you have designed a carry look ahead adder, or the, so previously we have designed this circuit. This is a full adder circuit. Then we have derived this expression for the C out. So here we have AB. We have the AC and BC. Okay, so this is the C in. So we can use this expression to design, let's say, a 4-bit adder. So this one is for a carry look ahead adder. So let's say we have this expression. So we have for CI plus 1. So we have AI, BI, AICI, BICI. Then here we factor out CI. Therefore, we have this expression. So let's say for AI, BI, so let's say that is equals to GI, and this expression, let's say this expression is for PI. So let's say G is for generate, and P is for propagate. Okay, so using this expression, so we have here now GI, AI, BI, then for PI, or P sub I, that is A sub I plus B sub I. Okay, so again we have the generate and propagate expression. So we want to expand this expression in terms of, let's say, we want to expand. Okay, so expanding. So we want to expand expression. So let's say in terms of, let's say stage I minus 1. So here we can, let's say, design a circuit. Let's say this is our full adder. So we can design 4-bit up to n-bit circuit. Okay? So using this model. Okay, so first stage, so let's say at stage I minus 1, so we want to expand the expression. Let's say for Ci plus 1, then we have I minus 1, so we have here C I minus 1 plus 1, therefore we have C sub I. Okay, so C sub I natin is coming from our original expression. So we have, let's say, C I plus 1. So we have GI plus PI CI. So remember, yung ating first expression, okay, CI plus 1, we have GI, PI, CI. So for C sub I, so we have GI plus PI, so substituting I minus 1 for CI plus 1, so we have GI minus 1 plus PI, that is PI minus 1, then we have CI minus 1. Okay? So we just take the expression CI and we substitute it in this CI. Then for some stage, let's say ending at 0, so yung complete stage natin. So let's say this is our let's say this is our stage 0, this is stage 3. So we have the expression for, okay, for some other stage or stages ending with stage 0. So our expression will become I plus 1. So we have GI plus PI GI minus 1 plus PI minus 1. We have GI minus 2. So P is generating, then P is propagating, then G is generating. So plus and so on, plus. So we have PI minus 1, and so on up to, let's say, P2, P1, G0, up to PI minus 1, up to P1, P0, C0. So let's use this expression to design a 4-bit other. Okay, so let's say for the given expression, so let's say this circuit. And let's say we have input. Let's say this is A0, B0, input A1, B1, A2, B2, B3, A3. Then we have the sum S0, this is S1, S2, S3. Then we have the carry in, C0, C1, C2, and C3. Then using the function that generates and propagate. So we can write the expression for, let's say, C out is equals to, so we have A3 and B3, A3, B3, plus, so we have the A3 plus B3 times, what's next, A2, B2 plus A3 plus B3, then we have A2 plus B2, then we have A1, B1, plus A3, B3, A2 plus B2, then we have A1 plus B1, then we have A0, and with B0, plus A3, B3, A2 plus B2, A1 plus B1, then we have A0 plus B0, then lastly we have A0, B0, then we have C in. Okay, so this is the expression we're going to use in our design. Let's say let's say module, let's say other 4-bit using behavioral modeling. So we have the inputs A, B, let's say C in, C out, and sum. So for the input, so we have the vector for A and B. So that is 4-bit. So we start at 3, 0. So we have A, B. So writing in this way, so we have A3, B3, B2, sorry. Oops. Okay, so for this one, so we have A3, A2, A1, A0. If we write, let's say, 0 to 3, so this means we have A0, A1, A2, A3. Okay, so be careful with declaring vector variable. Okay, so this is 3A, A3, A2, A1, A0. Then we have also input C in, the output sum, another output for C out. Then we have wires. Okay, so EB are wires. What else? So wire to C in. Then we have the registers. So reg sum. Also reg C out. So we can use the always block. So always let's see, always so inputs A or B or C in. Then let's say begin. So formula for the sum. What's the formula for the sum? So that is sum equals to A plus B plus C in. Okay? So that's the formula for the sum. Then for the C out, so the one we have derived, so we write A3 and B3, so that is in vectored form. So A3 and with B3. Then plus or we write A3 plus B3. So we write A3 or with B3. Then we have and with A2 and A2 and with B2. Then or, so we repeat again, A3 plus B3. Then we have also and it with A2 plus B2 now. So A2 plus B2. Then that is ANDed with and with A1 B1. Okay, then or, so A3 plus B3, then and with A2 or B2, then and with, we add A1 or B1. Then we add it with A0 and with B0. Then or, so lastly we have A3 plus B3 and with A2 or with B2, again and with A1 or B1. Then we're going to add A0, B0. So that is and with A0 or with B0. Then lastly we add it with C in. Okay, so that is the equivalent expression for C out. So begin, then end module. Okay, so medyo complicated using behavioral modeling. Okay, any question, class? So for the test picture, so we can use a simple test picture for this one. So again, I will shortcut ko na lang. Let's say I'm using initial, tapos I want to monitor. So inputs A, B, so we have here C in, C out, and the sum, comma, so we have A, comma B, C in, C out, then sum. Okay, so in this format will be displayed in your test picture. So again, initial, then begin. Let's say starting at time 0 nanosecond. So for input A, so that is 4-bit binary. Let's say our input is 0, 0, 1, 0. Then for B, I want to input, let's say 4-bit. I want to add, let's say 0, 1, 1, 0. Then let's say my first C in, so that is C in is equals to 1 bit. Let's say 1. Okay? So I'm adding here 0, 0, 1, 0 plus 0, 1, 1, 0 plus the carry in. I have the carry in 1. Okay? Then let's say I want to add another time. So time frame, let's say 10 nanosecond. I have input for A, let's say 1, 0, 1, 0. For B, 4-bit, 1, 1, 1, 0. C in, let's say 0 input. Let's say another time scale for A, 4-bit, let's say 1, 1, 0, 0. For B, let's say 0, 0, 1, 1. Then C in, let's say binary 1. And so on. Let's say 1 to stop. Okay, 10 nanoseconds stop. Then begin, end. Okay? So this one is for, again, sa test picture natin. So that is for writing or describing using behavioral modeling. So the other one is by structural modeling. So for structural modeling, let's read under this one. So that is under your laboratory exercise number 5. For structural modeling, so this is one of the useful methods describing digital circuit. So by using objects for instantiation to make a complete working circuit. So let's say we have already built a full adder circuit or module. So we can use that in structural modeling. So let's say we have already a UDP for AND gate, OR gate, etc. So again, we can also include that in our describing using structural modeling. So by instantiation, we mean, okay, so we instantiate objects. So the use of one or more lower level modules, including primitive logic, that are interconnected to construct higher level structural model. So for this example, I have here a module for D flip-flop or D flip-flop. Then this module will be used in some other synchronous or other sequential circuit. We're going to use dun sa ating susunod na mga activities. Okay, so first, let's continue designing 4-bit carry adder using structural modeling naman. So suppose again we are asked to design a 4-bit let's say ritual carry other. So we have these blocks, for example, for 4-bit. Let's say this is for B0. This is A0 input. This is for A1. This is for B1. Let's say this is B2. Input A2. A3. And B3. Then the sum 0. This is sum 1, sum 2, sum 3. So that is in vectored form. So we have here Cin. Then let's say this is C0. This is C1, C2. Then we have here C3. So we're going to design or describe this circuit using structural modeling. So let's say this is our full adder 1, 0, full adder 1, full adder 2, and full adder 3. So we already described full adder circuit. So remember, so meron na tayong module for full adder. So we can use instantiation, or we can instantiate that in structural modeling. So following this circuit, so we can describe, let's say, module, let's say, add ripple. Our module name is add ripple. So we have inputs A, B, C, and let's say Cin, and then sum, Cout. Okay? Then input, okay, vector 3, 0, AB. Cin is also an input, sum 3, 0. Then for the output, Cout. So next we define. So here we have internal nets. So C are internal, what we call internal net. So C0, C1, C2, C3. So we define, we call it internal nets or wires. So that is wire starting at 0 to 3, so that is 3, 0, C. Then we define the output. Okay, define output. So our output is, we have Cout is equal to C3. So we can use the assign keyword. So assign Cout equals to C3. Then we can now instantiate our full adder. So instantiate full adder by instantiate full adders. So it means we have already module. Let's say our module for full adder is FA. Let's say FA circuit. So let's say that is the name of our full adder module. So by instantiation, we can use this name, FA underscore circuit. So we write FA underscore circuit instantiate 0. So this one is our, let's say this is our 0 component, 1, 2, 3. So instantiate 0. So we have inputs A0, B0. We have the Cin, sum 0. What else? And we have the output C0. Okay? Then instantiate 1, so yung second full adder, so that is FA circuit int 1. Let's say we have A1, B1. Now we have here C0, C0. Then we have sum 1. Then carry out C1. Okay, next. The third full adder, FA underscore circuit instantiate 2. So we have A2, P2, then we have C1, sum 2, this is C2. Then FA circuit instantiate 3. So we have here A3, B3, then we have here C2, sum 3, then we have C3. Okay, so that ends of our module. So end module. So this is the module for 4-bit ripple carry adder. So this one is simpler. Then for the test bench or test picture, so you can use the one, ilan na yung ating test picture. So we have the for loop, the monitor, tapos yung initial begin. So you can choose among those test pictures. Then for your assignments, I want you to answer this one. This one is for subtraction. So let's say we have, we want to subtract, let's say 0 minus 0 is 0. Then 0 minus 1 is 1, but with borrow from the next higher ordered minuend. Okay, so we have the minuend minus, so this is our subtrahend, and then the difference. So 1 minus 0 gives us 1, then 1 minus 1 gives us a 0. So we can use here um, the complement method. So let's say we want to subtract, let's say, a minus b. So here we have minus b, so we can write it as a plus, first we get the first complement of b, then we add 1. For example, let's say we want to subtract, let's say 15 minus 96. So this gives us negative 81. Or if we want to perform using 2's complement, so yung 15 is 0, 0, 0, 0, 1, 1, 1, 1. Then 96, 1, 2, 4, 8, 64 plus 32 is 96. So 1, 2, 4, 8, 16, 32, 64, 0, 0, 0, 0. So we want to subtract. So using 2's complement, so kunin natin si first complement. So this is your B. So the first complement is 1, 0, 0. 1, 1, 1, 1, 1. So this is the first complement. Then plus 1. So 1 plus 1 is 2. This is 2, 2, 2, 2. 1, 0, 1. So this is now the 2's complement. Then if this is your A, so we add A plus this complement. So that is 0, 0, 0, 0, 1, 1, 1, 1 plus 1, 0, 1, 0, 0, 0, 0, 0. So this is 1, 1, 1, 1, 0, 1, 0, 1. So this is the same as negative 81. Okay? So we use this expression to, let's say, design. So this is your assignment. So we're going to design a 4-bit. Okay, assignment number 1. So you include it in your laboratory lab number 5. So yung first one is you design a 4-bit, let's say, subtractor. Okay, so using this expression, A minus B, A plus B prime plus 1. Then the next one is by designing a 4-bit other subtractor. So for the other subtractor, we're going to, let me draw the circuit. So you have here now a selector. So let's say 4-bit or 4 bits. So for input B, so we're going to XOR it with the selector. So selector, let's say that is your carry in. So let's say that is your M. Then you're going to XOR it with the B input. Okay, so this is your input B0. Then this is your A0. Then another XOR. This is your B1, and this is your A1. then XOR, so this is your B2 and A2, then XORed with, this is your B3, A3, then Cout, let's say this is Cout3, Cout2, Cout1, this is your Cout0. Then let's say this is your K0, K1, this is K2, and this is your vector K3 for the sum. Okay? So for M, let's say 0, so you're performing addition. For M is equals to 1, you're going to perform subtraction. Okay? So for XOR, so we have, let's say, para XOR natin. So let's say M tapos B. Let's say 0, 1, 0, 1, 0, 0, 1, 1. For 0, 0, this is 0, 1, 1, 0. Okay? So that's why we XOR it. So for zeros, input 0, 0. Okay. So this is your assignment. So include that in your laboratory number 5.